Hello my dear students, welcome to my YouTube channel that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the ionization energy. That's ionization energy. So now let's firstly understand what do we mean by ionization energy. It is the minimum amount of energy required to remove the most loosely bound electron from an isolated atom in the gaseous state of an element so as to convert it into gaseous monovalent ion. So what is ionization energy? It is the energy required to remove the most loosely bound electron from isolated atom in its gaseous state. So let me give you an example through a diagram. So this is the example that I have taken, and here what's the point? Here I have taken an example of an element, that's sodium, whose atomic number is 11. So what will be the configuration? It's 2 comma 8 comma 1. So I have taken the three shells within the, it's a nucleus plus Zd. This is the plus Zd nucleus, and I have taken the three shells, the first shell, the second shell, and the third shell. In the first shell we are having 2 electrons. I have made that the 2 red circles, you can see that the 2 red points, sorry. In the second shell I have taken the 8 electrons, that's the 8 red points, and the third shell I have taken the 1 electron, that's the 1 red point. So what is exactly ionization energy? It is the energy. I am writing what is ionization energy. It is the energy required by this electron to get ejected out from a sodium atom. That's called ionization energy. Why this electron only? Because it is the most loosely bound electron, that is the electron of the outermost shell. So it is the energy required by the outermost electron of an element to get ejected out of that atom. That's called ionization energy. So now let's discuss some points about it. Now, the ionization energy, the process of ionization energy can be represented as, we are having an metal atom in its gaseous state. When this metal atom will lose an electron, it's gonna form me M positive gaseous ion. So the energy accompanying this reaction is called the ionization energy. So I have written, it is also known as the first ionization energy, as metal atom has lost its first loosely bound electron. So it is also called the first ionization energy because the neutral metal atom, you can see that the metal atom is having zero charge in the reactant. The neutral metal atom has lost its first electron and has formed the M1 positive ion. So the energy required by any metal atom, or you can say any element, to lose its first electron is called the first ionization energy. Now let's come to the second point. Now when this M1 positive gaseous ion will lose its second electron, it's gonna form me M2 positive gaseous ion. The energy accompanying this reaction will be termed as second ionization energy because the M positive gaseous ion has lost its now second electron. So the energy required by metal unipositive ion to lose its second most loosely bound electron is called the second ionization energy. So it is the energy required by M1 positive ion to lose its second most loosely bound electron, that's called the second ionization energy. Now let's come to the next point. When any element loses its electron, the effective nuclear charge increase on rest of the electrons, and hence the size of that ion decreases with respect to the parent atom. Now if the size has decreased now, so the second most loosely bound electron is very tough to get ejected out. That means in the second electron the element will require more higher energy as comparatively that of the first electron. So we can say that it signifies that the first ionization energy is lower than the second ionization energy, which is further lower than the third ionization energy, because whenever an element loses an electron it form a unipositive ion. Now as the number of electron has decreased, the effective nuclear charge has increased, thereby decreasing the size. So it is very tough to now lose the second loosely bound electron from that unipositive ion. That's why the second ionization energy is greater as comparatively the first ionization energy. And the very same way, the third ionization energy is greater than the second ionization energy. Now, let's discuss some factors on which the ionization energy depends. Now, the topic is factors on which ionization energy depends. The very first factor is obviously the size of the atom. Smaller the size, more the electrons closer to the nucleus and its attractive pull. Hence, more energy is required to take electron out of that atom. Thereby, ionization energy will be greater if smaller the size of the atom. So you can here easily observe that the relationship that ionization energy is inversely proportional to the atomic size of the atom. Now let's come to the second point, the screening effect or the shielding effect. We have done this effect in the previous lecture videos. You can go back and see that lectures to understand this topic more clearly. Now, more the screening effect, the lesser is the effective nuclear charge on the outermost electron, and hence they are easy to get ejected out. That means if the screening effect is greater, the outermost electron will feel less effective nuclear charge, so the less energy is required for that electron to get ejected out. So we can say that ionization energy is again inversely proportional to the screening effect. More the screening effect, lesser the effective nuclear charge felt by the outermost electron, hence more easier will be for that electron to get ejected out, thereby less energy is required. So ionization energy will be lesser if the screening effect is greater. Now let's come to the third point, the effective nuclear charge. Now higher the effective nuclear charge on the outermost electrons, hence more energy will be required to eject them out. If the effective nuclear charge acting on the outermost electron, or you can say that what's the effective nuclear charge? It's the attractive force of the nucleus for the outermost electron. If that attractive force is greater, obviously it is more strongly held by the nucleus. The electrons are more strongly held by the nucleus, so higher energy will be required to eject for the ejection of that electron. So higher energy will be required for the ejection of that electrons. That means ionization energy is directly proportional to the effective nuclear charge. More the effective nuclear charge, more will be the ionization energy required, because there will be the greater force of attraction between the nucleus and the outermost electron. Now let's come to the fourth point, the half-filled and fully filled orbitals. The atoms having half-filled or fully filled orbitals are comparatively more stable. They have a stable electronic configuration. So more energy will be required to remove the electron from the such atoms. That means more the stable electronic configuration, more will be the ionization energy. It's a direct proportionality. Now let's come to the fifth point, the shape of the orbitals. Now we all know that we are having four types of orbitals, that's s orbitals, p orbitals, d orbitals and the f orbitals. Now the s orbital is more closer to the nucleus than the p orbital of the same subshell. Thus it is easier to remove the electron from the p in comparison to s orbital. So in general what will happen? Ionization energy will follow the following order. That means for s orbitals, ionization energy will be the higher, For P, it is somewhat lower, then D more lower, and then F, the more lower will be the ionization energy. Now, now let's discuss the trends of the ionization energy in the group and a period. Now, the trend of ionization energy down the group. Let me take an example. I'm taking an example of, let's take a group number 1. Here I'm taking group number 1. The group number 1 is hydrogen, lithium, sodium, potassium, rubidium, cesium, and the francium. Now, this will fall in period number 1, the period number 2, period number 3, period number 4, the 5, the 6, and the 7. Now we all know, as we move down the group, I'm writing, as we move down the group, what will happen? Firstly, the number of shells will increase. Thereby increasing the size. That means the atomic size will increase down the group. The atomic size will increase down the group. Then what next? Why atomic size is increasing? Because screening effect is decreasing down the group. Screening effect is increasing, the screening effect is increasing down the group. The screening effect is increasing, thereby effective nuclear charge will decrease. Effective nuclear charge decrease. That's why the atomic size increase down the group. The atomic size increase down the group. So all these reasons are supporting the fact that ionization energy will decrease down the group. Ionization energy will decrease down the group. Why so? Because as we move down the group, the number of shells increase, the atomic size increase, screening effect increase, thereby effective nuclear charge decrease. So all these factors support the ionization energy will decrease down the group, because the outermost electron will be very loosely bound to the nucleus. The outermost electron will feel very less effective nuclear charge, and there is also increasing size, so that electron will be very easier to be removed from that element. That's why ionization energy will decrease. The electron will get lost by the element at a very low energy. That's why we can say that ionization energy will decrease down the group. The ionization energy will decrease down the group. So that's about the group, the trend of ionization energy down the group. Now let's come to the next topic, the trend of ionization energy along a period. Let me take an example of period number 2. That's lithium, beryllium, boron, nitrogen, oxygen, carbon, oxygen, fluorine, and the neon. Now, from left to right, what are happening? From left to right, first of all, the shell remains the same. The shell number remains the same. Then what next? The screening effect will decrease. The screening effect will decrease. Effective nuclear charge will increase, due to which what will happen? If screening effect will decrease, that means effective nuclear charge will increase along a period. Charge will increase along a period, due to which what will happen? All this factor will contribute for the decrease in atomic size along a period. That's I'm writing. Atomic size will decrease the atomic size will decrease along the period. All these factors support the fact that outermost electron will be very closer to the nucleus and will be in the very strong nuclear pull of the nucleus, due to which it will be very difficult for that electron to get ejected out, or we can say that very high energy is required by that electron to get ejected out of that atom, thereby supporting a fact that ionization energy will increase along a period. Ionization energy will increase along the period. So what was the trend of the ionization energy along the group and a period? First of all, I'm repeating for the group. The ionization energy will decrease down the group because of increase in size, and in case of period we can say that ionization energy will increase along a period because of decrease in atomic size along a period. So now let's come back to the periodic table. Let's come to the periodic table. So this is the periodic table with the values of ionization energy along a period and along a group, and here you can easily observe that the ionization energy, first of all, the ionization energy increase down the group. The ionization energy is decreasing, the ionization energy is decreasing down the group. Ionization energy decrease down the group, and on the another hand, the ionization energy increase along a period. Ionization energy increase along the period. Hopefully you got the fact that ionization energy decrease down the group and ionization energy increase along the period. So let me make you understand this topic by a simple graph. Now in this graph, first of all, let me mark the group and the period. Now first of all, this is the graph of ionization energy and the atomic number, and you can easily see that the graph of ionization energy with the atomic number. Now let me mark a first of all period for you. This is the period. What I have told you in the previous point, that ionization energy increase along the period. So you can here easily observe that the ionization energy is increasing along the period. Now Let me mark the atomic number. That's the atomic number 3, atomic number 4, atomic number 5, 6, 7, 8, 9, and the 10. So along a period, ionization energy increase with the some exceptions that the atomic number 5 has a lower ionization energy than the 4, and the atomic number 8 has a lower ionization energy than the atomic number 7, which we are going to discuss in the next point. But here you just have to observe that ionization energy is increasing along a period. Now, now let's talk about the group. Let me delete this thing first. Now let's talk about the group. Now, first of all, what I have told you that ionization energy increase along a period. So that means at the end of the period we will be having the noble gases. So you can easily observe the maxima of any noble gas, the maxima in ionization energy of all the noble gases at the end of the each period. Now, now let's mark this like this, that ionization energy is decreasing down the group. You can easily observe that ionization energy is decreasing down the group, and you can easily observe the maxima for the ionization energy in case of any period is for the noble gases. Maxima of the ionization energy is for the noble gases in any period, and on the other hand, the minimum ionization energy in a period will be of the alkali metals, or we can say the group number 1, that's lithium, sodium, potassium, rubidium, cesium, and then radium. And in this case also you can easily observe that ionization energy is decreasing down the group. Again, this is the ionization energy is decreasing down the group for the group number 1 also, and for the group number 18 also. But in case of any period, the maximum ionization energy will be of the noble gases, which is the member of group number 18, and the minimum ionization energy is of the alkali metal, whereas the group number 1. In case of any period, what I'm talking about, in case of any period, let me mark this period. This is the period in which the maximum value is for the noble gas, and the minimum value is for the alkali metal. Let me take another example for the group period. That's the period number 3. Is the period number 3, and the maximum value for the ionization energy is of the argon, which is the member of the group number 18, the noble gas, and the minimum value is for the sodium, which is the member of the group number 1, that's the alkali metal. And the ionization energy always decrease down the group, ionization energy increase along the period. Now let's talk about the exception. Now this is the graph for the first ionization energy of the group number of the period number 2. First ionization energy of period number 2. Now here you can see that the minimum ionization energy is of the group number 1 member, that's the lithium, that's the atomic number 3, atomic number 4 for beryllium, then atomic number 5 for boron, then atomic number 6 carbon, atomic number 7 nitrogen, then atomic number 8 oxygen, then atomic number 9 fluorine, and then finally the noble gas, that's atomic number 10 neon. Here is the exception. What's the exception? That beryllium has a lower ionization energy, beryllium has a higher ionization energy than the boron. That's boron is having lower ionization energy than the beryllium, or we can say that oxygen is having lower ionization energy than the nitrogen. What's the exception? That boron has the lower ionization energy than the beryllium. On the other hand, oxygen has the lower ionization energy than the nitrogen. These two exceptions are not following the trend that ionization energy increase along the period. So now let's discuss these anomaly on our notes. I'm coming back to the notes over. Now, what's the exception? Exception is that boron has a lower ionization energy than the beryllium, but according to the rule, it must increase the ionization energy of boron is lesser than that of the ionization energy of the beryllium, and on the other hand the ionization energy of oxygen is lower than that of nitrogen is lower than that of the nitrogen. Sorry, the carbon and nitrogen got flipped. Now, I'm saying that exception is that the ionization energy of oxygen is lesser than that the ionization energy of the nitrogen. So now let's discuss about these 2 points. Let's talk about the beryllium and the boron first. So I'm talking about the reason. The ionization energy of boron is lesser than that of the ionization energy of the beryllium. Let's discuss this point. What's the atomic number of boron? 5. The configuration will be 1s2, 2s2, and the 2p1. What's the atomic number of beryllium? Is 4. The configuration will be 1s2 and the 2s2. Now, firstly, the electron which has to be lost by the beryllium is the s electron. I'm writing the electron to be lost by beryllium is s orbital electron. Now, as we all know that s orbitals s orbitals are more penetrated towards the nucleus, are more penetrated towards the nucleus, comma, hence more energy will be required, more energy will be required for their ejection, for their ejection. Hence beryllium has higher ionization energy than boron. Now let's talk about the boron now. In case of boron, the electron to be lost is of p subshell or p orbital. So we all know that p orbitals are less penetrated towards the nucleus, hence it will be easier to eject an p electron. So boron will have a lesser ionization energy than the beryllium. But on the other hand, the 2s electron, the 2s electron, the 2s electrons will shield, or you can say screen, the 2p electron from the nucleus, thereby decreasing the ionization energy boron, then beryllium. So these were the reasons why boron has lesser ionization energy comparatively beryllium. It's an exception. Now let's talk about the next point, why ionization energy of oxygen is lesser than that of the nitrogen. Now here let's talk about the electronic configurations. Atomic number 8, the configuration of oxygen will be 2s2 2p3. Is nitrogen 2p4, sorry, 2p4. For nitrogen atomic number is 7, configuration will be 2s2 2p3. Now let's focus on the 2p electrons, because electron to be lost is of the 2p for both oxygen and the nitrogen. I'm talking about nitrogen first. I'm marking the degenerate orbitals of the 2p, the 2px, 2py and the 2pz. Now according to the Hund's rule, firstly the all orbitals will get one electron each before pairing start, but here we were having the 3 electrons. We got the 3 electrons in the different subshells, different orbitals, sorry, in the different orbitals. Now what's this? This is half filled stable electronic configuration. This is half filled stable electronic configuration, due to which what will happen? It's a stable one, so ionization energy will increase because of the stable half-filled electronic configuration. But in case of oxygen, what's the problem with the oxygen? Let's talk about the oxygen. It's 2p4. Now 1, 2 and the 3. We got the 3 orbitals of the 2p, the degenerate orbitals 2px, 2py and 2pz. We have to fill the 4 electrons. So according to the Hund's rule, the first electron, the second electron, the third electron and the fourth electron. In case of oxygen, the 2 electrons are in the same orbital. In case of oxygen, the 2 electrons are in the same orbital, so they will be the inter-electronic repulsive forces, which was absent in nitrogen. So here will be inter-electronic repulsive forces between these 2 electrons, forces between electrons, due to which it will be easier to remove the electron, due to which it will become easier to lose electron. Hence, ionization energy of oxygen will decrease comparatively nitrogen, because in case of nitrogen there is not any inter-electronic repulsive forces and it's a stable electronic configuration. So the ionization energy of oxygen will be less than that of the nitrogen. So that's all about the ionization energy. It's a bit confusing topic. Please do listen to this lecture very carefully. I hope you all understood today's lecture. If any student wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.